All right, so we're going to begin our next unit, which is forces. This is going to really form one of the foundations of mechanics. All right, so there's really two major ways that we're going to look at and analyze things. One is forces, the other is going to be energy. So we're going to start talking about this one. We've talked a lot about kinematics, and that's going to still be an important piece, but this really gives us the why things move. Kinematics kind of told us how things move, forces tells us why. All right, so let's talk briefly about Isaac Newton, because the first thing we're going to talk about with forces is Newton's laws. So, Isaac Newton wrote three laws, which we're going to talk about in a second, describing the motion of all objects. He did a lot of weird things. He also practiced alchemy, trying to change lead into gold. On his mission to really understand the motion of objects, he invented calculus, despite what your math teachers may say. They'll say it's this guy Leibniz, but Leibniz actually copied from Newton. Newton was the one who actually invented calculus. He did a ton of stuff with optics. Really, really smart guy. One of the most famous physicists of all time, right there with Albert Einstein for sure. So before we talk about Newton's laws, let's talk for a second about what Newton's laws deal with, and that is forces. Okay, so a few important things about forces. Forces, the most basic definition, and really the only definition you need, are that forces are simply pushes or pulls. Okay, we don't need anything fancy to describe what forces are. Forces are just pushes and pulls that exist. A few important things regarding forces. Number one, forces are caused by objects. And this is going to be something really, really important as we go through this unit. But if you can't name an object exerting a force, then there is no force. So I will say that time and time again, you must be able to name an object that creates a force. And this kind of prevents, I'll tell you what people start getting into, is things like the force of moving or the force of sliding or the force of inertia, which is my ultimate pet peeve. But you have to be able to name an object that creates a force. All forces come from objects. Another really important thing is forces must be from an outside object, meaning that an object cannot exert a force on itself. All right. The example I always give is if you're floating out there in outer space, floating in the middle of nowhere with nothing around you, you're in a bit of trouble, okay? Because you're not going to be able to accelerate. You're not going to be able to do anything because you can't exert a force on yourself. You need another object in order to be able to push off of. All right, so objects can't exert forces on themselves. And the last thing is that forces usually require contact. We do have a few exceptions to this rule here. One is a force that you experience every day, and that is gravity. That force, which results from the Earth, by the way, that's the object. All right, so that's one notable exception. Magnets are another. All right, so there are a few forces that are non-contact forces, but most forces require contact. Last thing, forces are measured in units of newtons, obviously named after Isaac Newton, but that's going to be our unit here for forces. All right, so let's talk about Newton's first law. And here's what Newton originally said in his book, Principia. He said, every body preserves in its state of being at rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed thereon. All right. That was his original way of saying it. This is the law that has been turned into objects in motion stay in motion and objects at rest stay at rest, and eventually turned into that terrible commercial that was on a few years ago. This is also the law with inertia. I don't really like any of these definitions. Obviously, Newton's original words are fine, but it's kind of written in language you don't really use that much anymore. Here's what I always say for Newton's first law. Objects need an unbalanced force in order to accelerate. Okay? So we need an unbalanced force in order for the object to accelerate. If we have an unbalanced force, okay, it means the object will accelerate. If we have no unbalanced forces, so all of our forces are balanced, okay, that means we either are at rest or we are moving with constant velocity, meaning no acceleration. All right, so that's what that means. The reason why I have a problem with that objects in motion stay in motion and objects at rest stay at rest, two things. Number one, that is only true if there are no unbalanced forces, and that part gets left out a lot of times. And number two, it's not just that objects in motion stay in motion, it's that objects in motion travel at a constant velocity, not speeding up, not slowing down, not changing directions, unless there's an unbalanced force acting on that object. And that's why I always get bothered by that objects in motion stay in motion, objects at rest stay at rest. This explanation, though, right here, this explains all you need to know. Objects need an unbalanced force in order to accelerate. So if we have unbalanced forces acting on an object, that object will accelerate. If we have no unbalanced forces, the object will not accelerate, which means it will either stay at rest if it was initially at rest, or it will stay in motion at a constant velocity if it was already in motion. One really important thing, and we'll talk about this many more times in the coming days, is that objects do not need a force, do not need an unbalanced force to move. They need an unbalanced force to accelerate, to change something about their motion, and that's key. That word inertia, I don't particularly like that word, but it is a legitimate physics term. It simply describes the tendency of objects to stay in motion or to stay at rest. Okay, so inertia describes that characteristic that objects want to stay in motion at a constant velocity unless acted upon by an unbalanced force, or they want to stay at rest unless acted upon by an unbalanced force. All right. What inertia really measures is it's really a measure of mass, okay? Objects with more mass tend to resist changes in their motion, tend to resist acceleration more so. So that's really what it is measuring in a sense, but it simply describes this quality of objects. This is not an acceptable explanation, though, okay? On tests, quizzes, etc., if you get a problem or a conceptual question about Newton's first law and you say that it does so-and-so because of inertia, that's not an acceptable explanation. I will tell you that right now. I will give you 0 points for that. I might even actually take off extra points. If it's a 10-point question, I might give you -2 points if you simply say that inertia is the reason why it does it. Give me a real explanation talking about forces, talking about acceleration, talking about changes in motion. Don't just say inertia. All right, and my rant now is over. Two quick things about this, all right, or two quick examples here. The first is the tablecloth demo, which is a classic demo. If you very, very quickly pull a tablecloth out from underneath a set of plates, those plates will stay put if you do it quickly, because you have 0 or very, very little unbalanced force acting on those objects, and so they stay where they are. All right, they don't accelerate, they don't move in this case because they were initially at rest, so they remain at rest. The other one is this dog here that has gotten stuck in the seat of a car. The question I always ask, here's our car. All right, think for a second about what happened to the car that ultimately led to this dog being put in that position. So think for a second about what happened to the motion of the car that led to this situation. And there's two possible responses. The key is we accelerated forward. So the car accelerated forward due to an unbalanced force, while the dog had no unbalanced force acting on it, and so it stayed where it was. All right, and that's really the key, is that the car accelerated forward, so it slammed on the gas, all right, and accelerated forward because of an unbalanced force from the road. The dog stayed put, and that led to the dog being stuck in this seat. The other possible situation, and it's the same motion, okay, would be if the car was initially traveling backwards and slowed down to a stop, once again leading to a forward acceleration. All right, so either at rest and slamming on the gas to speed up in the positive direction, or traveling backwards and slamming on the brakes. Both of those lead to an acceleration to the right, okay, and the dog wants to maintain its state of motion, either being at rest or, okay, moving backwards. And when the car accelerates due to an unbalanced force, the dog does not, and that ultimately leads to the dog getting stuck. Newton's second law, what he originally said was the alteration of motion is ever proportional to the motive force impressed and is made in the direction of a right line in which that force is impressed. Once again, obviously Newton got it right, but not always the easiest way to understand it. I find that the second law is simply best said with an equation. Sum of the forces is equal to mass times acceleration. This is a big equation, ladies and gentlemen. This is probably one of the two most important equations that we will learn all year. And it's quite simple, which is actually very nice. So here's what it says. Here's what all this means. This letter here, that's the Greek letter sigma, which, if you remember from math class, we often use when we're doing a summation. So sigma means sum. All right, so sigma F, the sum of the forces, meaning we're going to add up all of the forces acting on an object and basically figure out how much unbalanced force, the amount of unbalanced force that we have. Okay. Another way of putting this is the net force. So if we had, and we'll do a basic example here, let's say we have 10 newtons of force acting to the right on an object, 3 newtons of force acting to the left. The sum of the forces would simply be 7 newtons, right? 10 plus negative 3 is how we're going to get that. So that tells us the amount of unbalanced force we have, right? Because this 3 newtons cancels out 3 of those 10 newtons, and we're left with 7 newtons going to the right as our unbalanced force, or our net force. So that's what that first term means, the sum of the forces, or the net force. And that's going to be equal to the mass of the object times the acceleration of the object. All right. I always think about it this way. The first law tells us that objects will accelerate if we have unbalanced forces. And the second law gives us that proportionality, that relationship between force, or unbalanced force, and acceleration. Should be noted real quick, this should be obvious, but the direction of the acceleration is always the same as the direction of the net force, or the direction of the unbalanced force. So in this case, we would be accelerating to the right because our unbalanced force is going to the right. We will do mathematical relationships, obviously, with this equation, but from a conceptual standpoint, Newton's second law tells us two things. Number one, that the net force, or the sum of the forces, the unbalanced force, whatever you want to call it, is directly proportional to the acceleration. So as our force, our net force increases, so does our acceleration. And as our net force decreases, so does our acceleration. The second conceptual piece we can get from this is that mass is inversely proportional to the acceleration. So as the mass increases, our acceleration decreases, and vice versa. And that makes sense. You've experienced this before. Objects with more mass are more difficult to accelerate. If you push a toy car and an actual car with the same force, you're going to see a lot more acceleration with the toy car, because the smaller mass means we're going to have a greater acceleration, and the bigger mass means we're going to have a smaller acceleration. Hence, they are inversely proportional. Just as a quick recap, as that net force goes up, so does our acceleration. As our net force goes down, so does our acceleration. When we're thinking about mass and acceleration, as mass goes up, acceleration goes down. And as mass goes down, acceleration goes up. All right, Newton's third law here tells us that to every action there is always an opposed and equal reaction, where the mutual action of two bodies upon each other are always equal and directed to contrary parts. This is the for every action there's an equal and opposite reaction law. I don't particularly like that way of saying it either. It should be noted here that when Newton says action, he's talking about force. Right? So here's how I always put it. You can't push something without it pushing back equally. That's what Newton's third law really tells us. Okay? If you push on something, it pushes back equally. Every single force has an equal pair in the opposite direction. So if you push on a wall, the wall pushes back on you. Okay? Anytime two objects push on each other, all right, those forces that they exert on each other are equal. So we talked about the car and the bug situation, where the car is driving down the highway and it collides with a bug. Okay, the bug goes splat on the windshield. The bug obviously dies. All right, the car doesn't even really notice. Okay, however, Newton's third law tells us that the car and the bug experience the same force. The force the bug exerts on the car equals the force the car exerts on the bug. The key difference and the reason why those two forces have very, very different impacts on the two objects is mass. All right. So even though the forces are the same, okay, the accelerations might be different because the masses of the objects are different. All right. So the bug might experience an enormous acceleration because its mass is so small, and that ultimately leads to the death of the bug. The car, on the other hand, has a huge mass, and so it doesn't even experience much of an acceleration at all. But the important thing is that both objects experience the same force. So I want to look quickly at a few examples of Newton's third law, of third law pairs, we call these, forces that are equal and opposite. All right. So if we have the situation where a car is driving down the road, what ends up happening ultimately is the tires of the car push backwards on the road, which leads to the road pushing forwards on the tires. All right. That is your third law pair, those equal and opposite forces that propel the car forward. When we have rockets taking off going to outer space, the rocket actually ejects gas out the back of the nozzle, so it pushes backwards on the gas, and the gas then pushes forwards on the rocket. All right. We have this person here getting a little workout here with a spring. The person pulls on the spring pulls back on the person. Lastly, we have Galileo here dropping objects off the Leaning Tower of Pisa. That's a true story. He actually did that. And we have the object, the ball falling, is being pulled down by the earth, but then the ball also pulls up on the earth. So we have earth pulling down on the ball pulling up on the earth. All right, so those are some examples of action-reaction pairs, or what I usually just refer to as Newton's third law pairs. One really, really important thing to note from the last slide is that all of those third law pairs act on different objects. So we have a collision here between A and B, and so we're going to have the force of A on object B, and then B is going to exert a force back on A, so the force of B on A. There is your third law pair. These two forces are going to be equal, but notice that those two forces act on different objects. This force of A on B is a force on object B. This force of B on A is a force on object A. I say this because sometimes we're going to want to identify third law pairs, and there will be situations where two forces acting on the same object happen to be equal, but they are not a third law pair. Third law pairs specifically are about the forces that exist between two objects. All right, one on the first object, the other on the second object. And those are the forces that we know are equal. Those are the forces that will always be equal and opposite, which is what the negative sign is for.